All right, ladies and gentlemen, welcome back to another installment of AP Chemistry Topics. Today we're going to take a look at the law of multiple proportions. So hopefully by now you've looked and you understand excuse me, Proust's law, or the law of definite proportions, where if we're looking at a singular molecule or a specific type of molecule, then we've got ratios that exist within that molecule, and we can look at the percent composition, we can check for purity, and we can figure out how much is there. Now, what happens when we have molecules that combine in different ratios? For example, if we go back to what we were looking at, and this interplay between carbon and oxygen, is carbon and oxygen always going to combine to form CO2? Well, the answer is no, right? I've got molecules of carbon monoxide, and I've got molecules of carbon dioxide, for example. And so what we're going to do is we're going to use the law of multiple proportions to start relating how these things and how these elements and atoms can combine and form different molecules. All right? And so here we go. States. So we're going to define the law of multiple proportions here. Make sure you get this down. When elements can react to form more than one compound. So when elements can react to form more than one compound, the weight of one element that combines with a fixed weight of another are small whole number ratios. All right? And so when elements, let me repeat it, when elements can react to form more than one compound, the weight of one element that combines with the fixed weight, and that fixed weight's important there, of another are small whole number ratios. All right, and so let's take an example and look at an example here. I'm going to erase a little bit here. I'm going to draw some molecules, and so you'll see a jump in the video here because I'm going to cut out the part when I'm drawing this out. I guess I could draw it with you here. So I've got a nitrogen. I'm going to draw another nitrogen. Let me give two nitrogens here, and then two here, and you're like, what else is going to be there, Mr. Doolin? Well, you just wait and see. Alright, now let me switch colors here. I'll do UT orange, so there we go. There's my oxygen. This molecule is going to have two oxygens. I want to make sure that I get those connected to somewhat show bonding. Let's see if I can do this. This one will have a singular oxygen. Here we've got 4. That looks like Mickey Mouse. And then the upside down Mickey Mouse. And then here we've got an oxygen in the middle, and then again 2 attached on each pole of the nitrogen. Alright, and so my molecules here, just to write them out, I've got NO, which is nitrogen monoxide. I've got NO2, N2O, N2O4, and N2O5. So again, it's just nitrogen-oxygen combinations, but they combine in different ratios, and so now we know we're in the law of multiple proportions. All right, so now remember, the definition is the weight of one element that combines relative to another. So what we need to take a look at first is we are going to look at the ratio of masses. All right, and I think I got this a little bit too close, so this one's going to go right over here. Don't get confused by that. And so I'm going to just look at the moles of nitrogen. So I've got mass of nitrogen is 14, oxygen would be 16, and again I'm just counting up how many nitrogens and oxygens are there and using average atomic mass, so nothing crazy. On my second one, again, mass of nitrogen is 14, oxygen in this one would be 32 because I have 2 oxygens, so 16 times 2 is 32. The next one here, I've got 2 nitrogens now, so I've got a mass of 28 in there, and oxygen would be 16. Here I've got 28 and 64, because I've got 1, 2, 3, 4 oxygens, so 4 times 16. And then on the last one, I've got 28 and 80. And so again, these are just ratios of masses. Now, something that you're going to see here is, remember, we want the weight of one element that combines with a fixed weight of another. Now, I'm going to do this in reference to nitrogen, and I really challenge you at the end of this to go back and redo it and see what it looks like with respect to oxygen. Now, we've got nitrogen all over the place. I've got 14s and I've got 28s. Remember, we want to do it with a fixed ratio. So in this particular case, I'm going to leave the 14s alone, and this one I'm going to divide by 2 to make it 14 and 8. I'm just going to put that in parentheses. 14 and 32, and 14 and 40. So now if we take a look here, what you'll start seeing, hopefully you catch it right off the bat, if I'm looking at 16, 32, 8, 32, and 40, they're all multiples of 8. They're going to be small whole number ratios. Now, specifically, and sometimes they're going to ask you to solve for this mathematically, so I'm going to go ahead and make actual ratios out of this. And again, I'm going to say grams of oxygen combining with 1 gram of nitrogen. And so now again, you're looking and you're like, oh, Mr. Doolin, what are you doing? I got 14 grams of nitrogen. Well, how do you turn 14 into 1? You divide it by 14. And so this goes into the idea of making ratios. I want to compare 2 different numbers to each other, divide them by the same number, right? The ratio stays the same. And so what I'm going to do is I'm going to go through here and I'm going to divide each of these by 14. So 14 divided by 14 is 1. 16 divided by 14 is 1.14. 14 divided by 14 for NO2, 1. 32 divided by 14, 2.29. And then I'm going to stay true to this, 1 to 0.571. That's a decimal there. And then 1 to 2.28, and 1 to 2.86. Now, when we get to this point, most people are going to look at this and they're going to like, oh man, this doesn't look like anything. When we had up there at 8 and 32 and 40, I could see that they were multiples. All right. So again, now we're going to have to create another ratio. What's the ratio of oxygen to other oxygens? And again, do what I just did. How did I make a ratio? I picked the smallest number, I divided by the smallest number. All right? And so if I'm looking here at these particular ones, this is the smallest amount of oxygen, which would be 0.571. And so I'm just going to divide everything out by 0.571. So 1.14 divided by 0.571 would be 2. This would be 4. 0.571 divided by itself is 1. This one would also be 4, and this one would be 5. So when we get down to this, we really see the small whole number ratios. Now, a lot of you are looking at this and you're going, what the heck, Mr. Doolin? We got this up here because if we go up here and we say, all right, 8's my smallest number, so there's 1. And then this one would be 4, because 32 divided by 8 is 4. 40 divided by 8 is 5. 32 divided by 8, 4. And then 16 divided by 8 would be 2. Notice they're the same. But a lot of the times we don't necessarily have those formulas. We don't have that particulate diagram, the drawing of the molecule to work with. We just have mass data. And so it's important to understand when we have mass data, we'll actually just create those ratios and divide everything out. All right? Okay, so we're almost done here. I'm just going to make sure that you understand if you had to draw a particulate diagram, particulate, and this is going to be a common theme in the class this year, is we're going to have to draw everything out at the atomic scale and make sure that we understand. So if I've got NO2, this is going to be nitrogen this time, and O. And then I've got, let's do N2O5. So I'm going to do my oxygen. I forget what thing I had for nitrogen here. It's close enough. So that's oxygen. Okay, so if we're looking at this, how do we look at the particulate diagrams and say, hey, these are going to obey the law of multiple proportions? All right, because it's easy when we know what the elements are, but what if I don't give you the elements and you don't know what the masses are, right? How do you know it follows that law of multiple proportions? Well, what you do, again, because remember, this is all in reference to one element, right? The mass of the other element that will combine with the fixed weight or fixed amount of the other one. So what you do in this particular case, I'm going to go ahead and switch it up here. I'm going to pick... no, let's pick nitrogen just to stay consistent with what we were just doing. is I'm going to pick nitrogen to be my reference point. Now, if I look here, this has 2 nitrogens, and this one only has 1 nitrogen. So what I need to do, I need to double this. So now I've got N, O, and O. So now I've got 2 nitrogens over here. So now my amount is the same. All right, the amount of nitrogen, the amount of my reference element is the same, and then I look at the oxygens. Are they small whole number ratios? Well, yeah, I've got 1, 2, 3, 4, 1, 2, 3, 4, 5. So I have a 4 to 5 ratio, and if we go back and we look at that, look back at what we just did in our notes, and you'll see that ratio holds true just by drawing out the particulate diagrams. All right, so don't get caught up in the math. Understand the concept of this. This is going to come back, and we'll see this come back in when we're doing molecular versus empirical formulas in the next couple of days. And if you have any questions about this, ladies and gentlemen, please come to tutorials. We're going to work with some of this stuff in class, where we'll deal with some hands-on activities that you'll be able to build stuff and take it back apart. So if you have any questions, again, come see me in tutorials. Otherwise, I will see you in class.